Hi everyone. In this lecture, we will discuss about the sinusoidal response to lossless second order systems. So these are the four transfer functions that we discussed in the last lecture, and we actually derived the impulse and step responses for all the four generalized transfer functions for second order lossless systems. Again, just to reiterate, so what do I mean by a second order lossless system is a system which has two poles on the imaginary axis, two complex poles, in fact two purely imaginary poles, okay, and all these systems have an infinite gain at omega, at the frequency omega equals omega naught, okay. The gain will be finite at other frequencies, or it can also go to 0, but at this omega equal to omega naught, which is the resonant frequency of this second order system, the gain is infinity. Now first I'm going to feed a sinusoid to each of those systems and then observe what kind of outcomes do we get in time domain. And we also will try to draw some intuitions from the answers that we get from the analysis of these systems. We are going to feed sinusoids and then we'll see the outputs, and from that we'll try to draw intuitions. So first I'll take the simplest. So this is the low pass second order lossless system. So I'm going to feed a sinusoid which is cos omega naught t. So I've chosen cos here with an amplitude say Vp cos omega naught t into u of t. I've chosen cos here. In the previous lectures I might have chosen sine. It's sinusoid at the end of the day. I'm just looking for a signal with an infinite gain at a single frequency. Okay, what do I mean by that is in frequency domain, because all its energy will be focused at a single frequency. Okay, the Fourier transform is going to contain impulses. I'm just trying to feed inputs of that kind. Now, for a sinusoid, Bp cos omega xt, omega x is the input frequency of the sinusoid. There are two cases which we'll analyze: when omega is not equal to omega naught, the resonant frequency, and when the omega x equals to the resonant frequency. So again, I'll resort to the Laplace transforms to solve this problem. So I'll take the Laplace transform of the input and then multiply it with the system transfer function. Okay. From this, we'd get Vp we'll actually have two terms in the denominator, a square plus omega naught square. So I'm again going to use partial fraction expansion for this, and I'd get okay. So from this, again, I'll take the s term inside, and if I take inverse Laplace transform of this expression, I'd get Vp h of 0 you'd get two cosine signals. Okay. So now when you fed as an input, you actually fed an input with frequency omega x, but at the output you have two frequencies, which is omega naught and omega x. You're getting omega naught because there is a finite energy in the signal at the frequency omega naught, and this system has an infinite gain at omega naught, so therefore you will be getting a finite power output. We discussed this in the previous lectures. Okay, so that's why you're actually having two frequencies. So this generally we are used to whenever you analyze a linear time invariant system, LTA system. Okay, so those systems you're always used to giving a sinusoidal input. The output frequency will also be the same as the input frequency. But here in these resonant systems with an infinite frequency, with an infinite gain at a certain frequency, we'll also get omega naught, the resonant frequency, along with the input. Okay, so this is the response if your omega x is not equal to omega naught, a general response for a low pass second order lossless system. Now I'm going to feed h of 0 a sinusoid of same frequency as the resonant frequency, and see what we get in that case. So again I just rearrange some terms, and I'm going to reduce this as okay. So again, we in one of the previous lectures we derived the inverse Laplace transform for this equation, which is actually t by 2 sine omega naught t into u of t, and we'd get, so if I feed a sinusoid as an input to the system, so this system is a low pass system with a resonant frequency at omega naught. If I feed a sinusoid here, what we are going to get here is an linearly a sinusoid. It starts at 0, and then the amplitude would increase linearly as time increases. Okay, so that's what we are going to get here, and we also saw that we also gave an intuitive explanation for this in one of the previous lectures. Again, for the sake of completeness, I'll just so we have just derived the sinusoidal response for a simple low pass system. So if I give a frequency, a sinusoid of frequency omega x, which is not equal to the resonant frequency, we just showed that we'd get one term which is same as the resonant, which is same as the input frequency, and we'll also get another term, another sinusoid, which will be the resonant frequency of the system. Okay, we already discussed this response. I just thought that, since we are doing a general response, a response for generalized transfer functions, I thought I'll just briefly talk about it. The next is our high pass response, which is h infinity into s by omega naught the whole square by 1 plus s by omega naught the whole square. So here h infinity is the high frequency gain. So if we already drew this response in the previous lecture. So if I draw this, the high frequency gain here is h infinity. Okay, and this also has a resonant frequency at omega naught. Now I'm going to feed a sinusoid. So I'll write the Laplace transform of the sinusoid which I'm going to feed to this. So this would be s square plus omega x square. I'm going to feed a sinusoid of frequency omega x, which is not equal to omega naught. Now this function, I'll rewrite it as, I'll rearrange the terms and write this as a simpler expression. So here you can actually see this. So this is nothing but 1 minus a low pass transfer function. So intuitively it should make sense, because if you subtract, this is like an all pass transfer function which passes all the frequencies, and this is like a low pass transfer function which only passes low frequencies. So when you subtract the two, you'd get a high pass response. Again, this is a well-known thing in filter theory. Now I'm just going to take this term inside, and we already know, and then take the inverse Laplace transform. So you'd get Vp h infinity into cos omega xt. Okay, now this term should intuitively sound fine, because this is the high frequency gain. So a cos input at t equal to 0 is going to behave like a step input, because this is cos omega x into t. So it's going to be like a step input here. So the instant you're going to feed this input, that will get multiplied by the high frequency gain. We already discussed, whenever you feed a step input at t equal to 0, it's like a high frequency sinusoid. So the gain for that is going to be h infinity. So at t equal to 0, it will be just multiplied by h infinity, and you'll get the cos omega t as it is. But there is also another term. Okay, so this term is same as the low pass term. So this will be like the response of a low pass filter. We just discussed in the previous problem, if I feed a sinusoid of frequency omega x square, I'm just going to directly write the final result here. So this will be minus Vp, okay, into omega naught square upon omega naught square minus omega x square into cos of omega xt minus cos of omega naught t into u of t. Now at t equal to 0, this term will be 0. So you would get simply, the output is going to be a sinusoid. It will look like a sine wave, cosine wave, with a gain of h of infinity. Previously it was Vp, it will be Vp into h of infinity. That's the only difference. Okay, and this again, we said that this is h of infinity from intuition, because as soon as you apply a step sine wave, you're going to multiply that with the infinite frequency, the high frequency gain, which is h infinity in this case. So this part should actually sound intuitive. Now, what happens when you feed a sine wave of same frequency? Again, we are going to get the same signal here, very similar response as we got for a low pass response. For low pass, we only got this term here, okay, which was 0 at t equal to 0, because for a low pass system, the high frequency gain is 0, the h infinity is 0. So therefore, you would not get any output instantly when you apply a cosine signal. It's going to start off from 0, and then it's going to last like a sinusoid. On the other hand, for a high pass filter, for a high pass second order lossless system, you are going to get a sine wave immediately. I mean, you are going to get a replicated version of the input sine wave immediately at t equal to 0. After that, the waveform will look different. But at t equal to 0 and in the vicinity of t equal to 0, okay, the input will be just multiplied by h infinity. And that comes because of the high pass nature of the system. Okay, the output can actually have sudden changes. When I say the high pass nature of the system, all it means is that the output can actually have sudden changes. So now, if I apply a sine wave of frequency omega x equals omega naught, then what will be the response in that case? So here, I'll just write the Laplace transforms directly. Now we have split the input Laplace transform, the transfer function of the system, as a constant minus a low pass system. Okay, and I'm going to feed this to this, so you'll actually get h infinity Vp cos omega naught t, okay, minus when this is being fed to this, so we'll actually get h infinity omega naught t by 2 sine omega naught t into u of t. Okay, so this is the response we'll be getting. I think we got a similar response for a low pass filter. Okay, there was a small mistake in the equation here. We'd actually get omega naught into t. Okay, that won't be an omega naught square. When you write it, I should take omega naught term here. The inverse Laplace transform of this term here is actually t into t by 2. In fact, there is a half term here, t by 2 into sine omega naught t. Okay. So here as well, you would get this term here. Now again, you can see this here. This function here actually starts off as it's a linearly increasing function, but it starts at 0. At t equal to 0, it actually starts at 0, and then it goes off as an increasing sine wave. This term, on the other hand, is actually a cosine which starts at a value of h of infinity into Vp at t equal to 0, and then it lasts forever. So the only difference between the low pass is that if the low pass output would actually start at 0, in this case you have to subtract this waveform minus this. Okay, that will be your output response. There is Vp here as well. Okay, the difference here is that the input will actually start at h infinity into Vp. If h infinity is 1, your output will also be starting at it will be the same exact replica of the input multiplied by the high frequency gain. Okay, if I consider the high frequency gain to be 1, it will be the same replica of the input at t equal to 0, around the vicinity of t greater than 0. Okay, after that it will be, this part of this, the second term will dominate, because that amplitude of the second term is going to grow linearly to infinity eventually. So that term will start dominating. Okay, so this is nothing but this is the impulse. If it was a low pass filter, if it's just an all pass filter with a gain h infinity, The first term is what you would be getting as an output. The second term is the low pass response. So you are subtracting the all pass minus the low pass, you get the high pass response. Okay. So again, when I feed a sinusoid, again whether it's a high pass or a low pass, both the functions, they are lossless second order systems. Both these systems have, they both have the same resonant frequency. That is, the transfer function blows up to infinity at omega equal to omega naught. So you are going to have a growing sinusoid for both these systems when you feed an input whose frequency is equal to the resonant frequency. The third one, this is the most interesting part, which is the system which actually has a 0 at omega equal to omega z. Okay, so in this case, I am going to feed a sinusoid again, which is cos of omega xt into u of t. I'll assume the amplitude to be 1. Okay, I'm going to feed this sinusoid as an input to this system. Now there are three possibilities here. One, omega x is not equal to both omega z and omega naught. The second possibility is when omega equals omega z. Okay. The third possibility is when omega x equals omega naught. And omega x, obviously omega naught is not equal to omega z, because otherwise it's just a constant function. So we have three possible inputs which we can feed to the system. So to solve this, I can write this. We have already written this transfer function with a real, with a zero, with a complex zero, as a sum of a low pass and a high pass transfer functions. We have already done this in the previous lectures. So I'm just going to write it in that way. So you can write it as h of 0 by 1 plus s by omega naught the whole square plus h of 0 into omega naught by omega z the whole square into s upon omega naught the whole square by 1 plus s by omega naught the whole square. Okay, so this term here, it's a low pass term and this is a high pass term. So we have to now feed a sine wave. First we'll feed a sine wave of frequency omega x, which is not equal to both omega naught and omega z. Okay, I've called this term h0 into omega naught by omega z as h infinity, the high frequency gain, because this system has both a 0 and a pole. Okay, both are resonant, because a 0, really the transfer function actually goes to 0 at 0 at omega z, and it goes to infinity at omega naught. But at very high frequencies, where your omega is much greater than both omega naught and omega z, the transfer function will reach a constant value, and that constant value here is h infinity. Okay, and in terms of the low frequency gain, which is h of 0, and you can also express the high frequency gain in terms of the low frequency gain, which is this here. So now if I'm feeding a sinusoid of frequency omega x to this system, we already know the kind of output we are going to get. So I'm going to directly write that. So if I'm going to feed a sinusoid of frequency omega x, we are going to get omega naught square by omega naught square minus omega x square. I have already derived this in the previous problems. So you would get both the sinusoid of input frequency, and you'll also have a sinusoid at the resonant frequency for the first term. The second term we said can be again split as a constant and a low pass term. So I'm going to directly write that as h infinity cos omega xt into u of t plus, this is minus, we have already done this result in the previous problem, so I'm just directly going to code those results. So you get h of infinity into omega naught square by omega naught square minus omega x square into this whole term here. Okay, so that I can rewrite it as h of 0 minus h of infinity into omega naught square by omega naught square minus omega x square into cos of omega xt minus cos of omega naught t, plus you would have h infinity into cos of omega xt into u of t. Again, this term here represents the the high frequency nature of the circuit, where the gain of this system is actually constant, which is h infinity. That's why when I fed a sine wave which is going to suddenly change at t equal to 0, this term here is going to be 0. Okay, both the cosine functions will just start to, both of them will be 1 at t equal to 0, so the difference between the two will actually be 0. This term will actually just multiply the input sinusoid with again h infinity, and you would get that as an output. Okay. Now we will take a very interesting case when omega x equals omega z. So the transfer function is actually 1 by s plus omega z, 1 plus s by omega z the whole square by omega naught the whole square, and again this would be h of 0. Now we already know this transfer function is, I'll draw it for the case when omega z is less than omega naught. So first you will encounter 0, and you will again encounter a pole at omega naught and 0 at omega z. So here if you look at the magnitude of the transfer function, the gain of the transfer function is exactly equal to 0. At omega equal to omega z, the gain is exactly equal to 0. So which means if I feed a sinusoid at this frequency to this system, whose frequency is cos omega zt, okay, into u of t as an input to this system, you should not get any sine wave at the output. So that's what intuition says. So we'll try to see mathematically what is the output response that we'll be getting. So again, I'll use the Laplace transform of this. This is, in this case, it's s by s square plus omega z square into h of 0. So this can be written as 1 plus s by omega z the whole square, or I'll just write this in simplified terms. So this function can also be written as s square plus omega z square by s square plus omega naught square into omega naught by omega z the whole square. Okay. Now this term I'm going to call it h infinity. This is just other way of writing the same transfer function. Okay, using h infinity, which is the high frequency gain. This is using the low frequency gain. So at omega equal to 0, you will get h of 0 as the value. Okay. Now h infinity into s square plus omega z square by s square plus omega naught square is the second order lossless transfer function written using the high frequency gain h infinity. Now if I am going to multiply this with the input Laplace transform, so these two terms would cancel out. Okay. So now you would be left with h infinity into s by s square plus omega naught square. So this, taking the inverse Laplace transform, so I'd get h infinity into cos omega naught t into u of t. So now you actually fed a sine wave of frequency omega z, but at the output you don't have a frequency omega. There is no output at omega 0, omega z. Okay, the output contains only one frequency, which is omega naught here. Okay. So for any LTI system with a finite gain at all the frequencies, this is not possible. Okay. Only an LTI system which has a 0, I mean, for example, if I had given this to a system of this type, 1 plus s by omega z the whole square, okay, then yes, even then you would not get any sine wave as an output for the system. Okay. But this system is not realizable using passive circuits. You need active circuits to realize a system of this type. Okay. So here, this is one interesting example where we got an output whose frequency was equal to omega naught, but the input frequency omega, I'll call it omega A as input frequency, was omega Z. And the third case, the final case, the third case is actually when the input frequency of the sinusoid is actually omega naught. So I'm going to feed cos omega naught t into u of t. Again, since the gain of the system is infinity at the frequency, we should expect to get an infinite frequency sinusoid if I feed this as an input. So again, I'm going to write this as h of 0 by, omega naught, h of 0 so this function will again split it up as and we already know the response for both of these. If I feed a sinusoid which is cos omega naught t into u of t to this system, we are going to get an exponentially increasing sinusoid, so whose amplitude is going to be increasing linearly. We'd get omega naught t by 2 sine omega naught t into u of t, okay, into h of 0. Again here it will be plus h infinity into cos of omega naught t into u of t, minus, as we said, this can be split up as a low pass and a high pass. We have already derived the expression for this, so I'm just directly quoting those results. You'll again get h infinity into omega naught t by 2 sine omega naught t. So this again reduces to h infinity cos of omega naught t into u of t plus omega naught t by 2 into sine omega naught t into u of t. Okay, so you're going to have a sinusoid which is going to change suddenly at t equal to 0, and this term will increase linearly with time. Okay, so it will be a sum of two responses, a sinusoid multiplied by h infinity, the infinite frequency gain, plus a linearly increasing sinusoid. Here it is going to start at 0, okay, and the amplitude is going to be the slope with which it will raise will be omega naught into h of 0 minus h infinity by 2. Okay, this is the envelope slope, the amplitude slope, the slope of the amplitude of the sine wave. So, and the last transfer function is the band pass transfer function, which is again this function we have already derived this. This is nothing but a parallel LC circuit. Okay, so this we have already derived extensively in one of the previous lectures. So I'll just directly tell you what to expect. So if I feed a sinusoid of frequency cos omega x t, where omega x is not equal to omega naught, then of course we are going to get a term of this type. We are going to get cos omega x t minus cos omega naught t, okay, with some constant here. So again, this you can very easily, we have already derived it in one of the previous lectures, so I am not doing that now. So this is the kind of response that you would be getting for this system if I feed cos omega x t. Again, the high frequency gain of this system is 0. H infinity is 0 for this, because this function is going to look like this. Okay, that's why we don't see any, an extra cos term. We see those extra cos terms only in in functions which has a 0, or we see it in a high pass transfer function. Okay, we don't see it in low pass and band pass responses, because for both these responses the high frequency gain H infinity is actually 0. Okay, so this all I'm trying to say is this function starts at t equal to 0, it starts at 0. Okay, so when you feed a frequency of signal of frequency omega x, you are going to get both omega x and omega naught at the output. Now similarly, when you feed a sine wave of frequency omega naught, in this example, instead of cos, I can just write it as sine omega naught t. I mean, the expressions will be slightly different for cos in this example. So I took sine omega naught t in the previous examples and solved it in one of the previous lectures. Again, if I'm going to feed a sine wave to this system, we are again going to get a term like this. We are going to get something like omega naught t by 2, or I'll just okay, with some constant again this constant is different from this one here. So we will be actually getting a sine wave, again a linearly increasing sine wave, if I feed a sine wave of frequency equal to the resonant frequency of this system. So this is again, we have derived this result in the previous lecture, so I'm just directly writing the final result. So you'll have a linearly increasing sine wave multiplied by some constant here. So that's all about the response of sinusoidal response of lossless second order systems. So we have derived some general results for lossless second order systems. So once you know the transfer function, so we know how to calculate by now the impulse, step and sinusoidal response for any general second order lossless transfer functions. So in the next lecture, we'll actually see how to derive these transfer functions by inspection. By merely inspecting a circuit, how can we actually derive these transfer functions? So I'll stop at this point.